Yeah, sure. Let's make a start. Okay, so I guess let K be a commutative ring. So I'll just get this out there, and then I'll give an intro to the talk. Ring and K algebra. And soon we're going to assume that K is a field of characteristic 0 and R is a polynomial ring. So it probably doesn't do any harm to just start thinking about that from the top. And let T be a sequence in R. So last talk we constructed a strong deformation retract involving the causal complex of T. And this construction relied on the existence of certain K linear maps, right? So we had these maps T del T1 through to del T n from R to R, which together we referred to as a system of T derivatives. So in this talk, or in this talk and probably the next talk, we're going to show that these maps exist under certain assumptions on T and that they can be computed algorithmically. So let's recall the definition of this system of T derivatives. So just a reminder to let K T be the K algebra generated by the elements of the sequence, including and also 1. Okay, and then we had this definition from last time. So given T, system of T derivatives are K linear maps from R to R, satisfying the following. So first of all, each element of R can be written uniquely in the form F is the sum of the sum over all sort of multi-indexes of RU, T to the U, right? And weird. By this I mean T1 to the U1 through Tn to the Un. So okay, so it needs some conditions on these coefficients, so such that the coefficients each RU lives in the common kernel of all of these del Ti maps, right? And I guess finitely many RU are non-zero. So this is actually a sum. Okay. Second of all, we have that del Ti works on the powers of T like so. So it does exactly what you'd expect differentiation to do. Where here by EI, I mean this thing. So we've got a 1 in the ith position and zeros everywhere else. And also embedded in this statement, we understand that like 0 times Ti to the negative 1 is just 0, right? Just for notational convenience. And then I've run out of space, so I guess we'll go take a look at board number 3, the bottom of board number 3. So our third condition is for F in KT now and r in the kernel, so one of the coefficients, we have that del Ti of Rf is R times del Ti of F. Okay. Okay, so that's what we're aiming to.
Could you repeat the last line of the first condition? I can't quite read it.
Yeah, sure. Let me just walk over so it's recorded. So in this last line, we're saying these coefficients here, that they lie in the kernel of all of the del Ti maps, and also that finitely many of these things are non-zero, right? Because just so this is a sum, right? Not anything else.
Yep. Okay.
Yep. Okay, cool. So that's what we're aiming to define. We're aiming to take in a sequence, a sequence of this form, and generate a system of T derivatives. Okay, so let's take a look at the. I think I might be short on board space this talk, so let's take a look at board number 4, I guess. So now suppose that R is a polynomial ring. Okay, so when so I guess we'll sketch what we're doing, right? So when n is equal to m, so the length of our sequence is equal to the number of variables in our polynomial ring, and t is the variables in our polynomial ring, then this construction is going to recover the usual partial derivative maps. So in other words, our goal is to generalize taking the notion of taking partial derivatives with respect to this sequence to taking partial derivatives with respect to other sequences in Kx, right? And before we get into it, I thought I'd give a bit of motivation for so this generalization is based on Euclidean division. And before we get into that, I thought I'd give a bit of motivation for why we sort of might try to relate these kind of things. Okay, so for simplicity, consider the one variable case. So Kx is just a univariate polynomial ring. Okay, and let F be a polynomial. So given another variable y, one can show in the polynomial ring Kxy that we have the following relation, sort of inspired by, I guess, Taylor's theorem. So that f of x is equal to this sum from 0, I guess, to infinity 1 on p factorial of f p y x minus y to the p, right? Where this thing is dp dx to the p, right? So the pth partial derivative of f with respect to the variable, the single variable x, right? Okay, and also notice that this is, despite this thing up here, this is the stuff on the right hand side is a polynomial, right? Because eventually these partial derivatives are going to be 0. So one can show this, right? And essentially, you show this for the way to show this is to show that this is true for the case that f is a power of x. And then you observe that both the left-hand side and the right-hand side are k-linear, right? They're k-linear functions. So you can then extend this to all polynomials in the polynomial ring. Yes, k-linear functions of a polynomial. Yeah. Okay. Okay. So that's sort of cool. I guess it's like a version of Taylor's theorem. And what we can do is we can rearrange it, right? So we could rearrange this and bring the other variable to the other side and obtain the expression like so. So what this is essentially saying, in other words, the remainder of f of x subtract f of y divided by x minus y squared is the derivative of f, right? As a polynomial in y, right? And we can show sort of similar versions of this in the multivariate case. It's not as simple as just saying take the remainder of f of x minus f of y divided by this thing in the multivariate case, but similarly, you can show that you've got these. You have this sort of Taylor's-like theorem, and the coefficients of this thing are going to give you the derivatives of f with respect to the different variables. And the point is you can calculate these, or what we're going to show now is that you can calculate these coefficients in this sort of Taylor-like expansion using the division algorithm that we covered in the MAG seminars. Okay.
So it's super tiny, but I think there's a small typo, just p minus 2 here, right?
Oh, yep. Good point. Thanks.
Okay.
Yep. Okay. Any other comments or questions? Cool. Okay. So the task for today is to so let's go back to the first board. The task for today is to prove a corollary of the division algorithm in a multivariate polynomial ring. And I think that's probably all we're going to have time for. And then the next session, we'll start talking about actually constructing these maps. Okay, so for that to work, let K be a field now. And we're going to begin by recalling some of these concepts of polynomial division, related to polynomial division in KX, in the multivariate polynomial ring KX. So we have monomial in KX is anything in the set right? So any monomial and monomial ordering is well-founded total order relation on this set with the property that U less than V implies U plus W is less than V plus W for all U, V, W. And like, a typical example, the ones we looked at in MAG a lot, say, for example, is like the lexicographic ordering on n to the n. Okay. So if f is a polynomial in kx, right? So we have something like this. Then so finitely many. Any cu to the kxu is a term of f. I guess any cxu such that cu is not equal to 0 is called a term of f. And given a monomial ordering on kx, if f is not 0, we define the multi-degree of f to be the maximum of the powers of the terms of f, or the powers of the terms of f, right? So, okay, where this maximum is taken with respect to our chosen monomial ordering. And if we take, say, u star to be the multi-degree of f, then the leading term of f with respect to the given monomial ordering is the term cu star x to the c. Oops. X to the u star. And the leading coefficient is just this cu star here as well. Okay. Okay. We also need to recall the properties of this division algorithm. So I'll give this on. I won't remind you of how the division algorithm works, but it's good. We need to know what its properties are. So I'll do that on the bottom of the third board. So theorem. Actually, I'm not going to have space here. I'm just going to go to the other board. So on the fourth board now. So theorem, given, say, f and g1 through to g, say, m in kx. And suppose we've got a monomial ordering on kx, and given this monomial ordering, the division algorithm produces polynomials r, q1 through qm, such that they satisfy the following conditions. So first of all, we have that f is this thing. Right. Second of all, none of the terms in R are divisible by any of the leading terms of the GI, the things we're dividing f by. And then 3, for all, say, I equals 1 through m, if qi is not 0, then the multi-degree of f is greater or equal to the multi-degree of Qi times Gi. Right? Okay. So the corollary we're going to prove is that we can iterate this division algorithm in order to completely divide these coefficients, so these Qi, appearing in this output of the division algorithm. Okay, so if you want to take a look at board number 2, that's what I've got written up here, right? So we'll talk through how this works, right? Okay, so it kind of works how you'd expect. You divide f by your divisors, by the G1 through Gm, and then you just you take the coefficients that you get and you just divide them again and you divide them again, and I guess there's something to prove here that this process actually terminates, right? So okay, the way I've got things set up here, we've got a set of polynomials and sort of indexes, which I'm calling Q, and Q is going to hold the coefficients, so the stuff that's generated by the division algorithm, and R is going to hold the remainder terms, right? And then as long as we've still got coefficients to divide, then we're going to do the following, right? We're going to go through every single so polynomial and index in that set, and we're going to apply the division algorithm to obtain these polynomials which satisfy the properties of the division algorithm, right? So that's all this sentence is saying. And then we're going to go through and we're going to add them to this set, right? This set of new divisors to these new coefficients to divide later on, right? And then with this remainder, we're also going to add that to the set R, right? This index, so this U index, lives in the indexing set for our so n to the m, right? So the indexing set for the divisors, right? And it's keeping track of what divisors end up in the product that should be multiplying this particular term in an expression for f, right? So if we had, 1, 1, 1 R living in our set, R, big R, then that would tell us that the term R times G1, G2, G3 would appear in that set. Similarly, if this was now a 2, then we would have a squared here, right? Okay, so that's the idea of what's going on. And then before we replace this, before we replace Q, our original Q with this new Q, we're going to go through and collect terms, right? And that basically says for stuff that is being multiplied by the same, view these things as coefficients of these polynomials in the GI, and just collect the terms exactly as you would if you were doing this, by hand algebraically. I'm really far zoomed out. I don't know how that's happened. Okay, all good. Can anyone still hear me? Yeah. Yeah, okay,
yeah,
cool.
I can still hear you.
Cool. Sorry, I closed the board and I was like sitting way high above the map. Okay. Okay. So yeah, and then just for completeness, I've shown the collect terms sort of function on the board to the right of this board. So basically, yeah, we go through every single term in the input. We look at all the indexes appearing in this set, and we let all the polynomials, we consider all the polynomials which appear with that index, we add them all together, and if they're non-zero, then we add them to the set, and then we just return that set, and that becomes our new Q. Okay, are there any questions about this algorithm before we go on to prove that it terminates? Okay, cool. All right, so let's take a look at board number 1. And we'll clear this board. So I guess now we need to prove theorem. This algorithm terminates and produces the desired output. Okay. So proof. So as for showing that it produces the desired output, essentially, this boils down to showing that at every single stage of our algorithm, the following equation is true, right? We can take all the UR in R and write, I guess, this is a bit messy, I suppose, but I guess it makes sense. RU to the G to the U plus U Q in Q is Q G to the U, right? You can show, and I think intuitively it makes sense that we have this expression being true at every single stage that the algorithm is running, right? And then we note that, well, if the algorithm terminates, then it terminates when Q is empty. So we have just this component, right? And this satisfies the properties we want it to, right? So we have these coefficients coefficients such that the leading terms of these GI don't divide any of their terms, right? So it's in the right form for our output, right? Okay, I've written up a more detailed sort of some more detailed notes on this in the notes for this talk, but I think I might just leave that as is for the spoken sort of version. Okay, so now we need to prove termination. Okay, so we're going to abuse notation and write that Q is in okay, so sorry, I need to introduce something first. Let's Qn be the value of, say, Q on iteration number n, right? Okay, and we're going to abuse notation and write that Q, a polynomial Q, is in Qn. That this is going to be true if and only if that UQ is in Qn for some U, right? So we basically forget about the indices, right? Now we're going to define a number, or rather a index Bn, which is going to be the maximum of the multi-degrees of all the polynomials appearing in Qn, right? And basically what we're going to do is we're going to show that this quantity is strictly decreasing as n increases with respect to the monomial ordering. And because monomial orderings are well-founded, this means that eventually this must terminate, right? Okay. I guess I don't really want to get rid of the algorithm yet, but I can probably get rid of this collect terms function. So I'm gonna do that. Okay. I guess I'm green over here. Let Q be an element of Qn minus 1. Let P1 through Pm be the polynomials computed from Q in this step that we apply the division algorithm. Okay. Now we know that from the division algorithm theorem that the multi-degree of Q is strictly greater than the multi-degree of Pi Gi for all I, assuming these things are non-zero. If any of these are non-zero, then it doesn't get added to the next set anyway, so it's okay. So if Gi is non-constant, we have a strict inequality here. Okay. Oh, sure. There we go. Okay. Okay. So what this says is that that this Bn minus 1 quantity, right? Because this is the maximum over all these multi-degrees of these Qi, is strictly greater than the multi-degree of Pi. Okay. Now the elements now the elements of say Qn consist of sums of such Pi, right? So possibly generated, well, definitely generated from different versions of different elements of this Qn minus 1 set, but they're all generated in the same way, and they all satisfy this condition here, right? And the elements of Qn consist of sums of such things, right? And I think it was a lemma in Cox, Little and O'Shea, or maybe it was an exercise in Mag, I'm not sure, that we have this relation, right? That the multi-degree of, say, a polynomial S, oh, I probably shouldn't use S and T, hey? That a polynomial H and H prime, the sum of the multi-degree of the sum of those things is less than or equal to the multi-degree of the, oh, hold on, no, it's not, it's less than or equal to the maximum of the multi-degree of H. And H prime. Okay. Okay, so it follows that for all Q prime in Qn, that we have that the multi-degree of Q prime is strictly less than Bn minus 1, which gives us that Bn is strictly less than Bn minus 1. And by appealing to the well-foundedness of the monomial orderings, this implies that the algorithm terminates. Okay. Any questions about any of that? I think I might leave it here. It's sort of a natural midpoint of the talk, and I sort of got through this a bit quicker than I thought I was going to. And there's about one talk's worth left of notes to come, and it's more sort of coherent if I sort of end it here. So I think that's it for the talk today.
Okay, no problem. Yeah, I don't think I have any questions. That was good.
Cool. Yep, sounds good.
All right, I'll see you guys then.
See ya.
Yeah. Thanks, Ron.
No worries.
Wait, why are we on Teams? What happened?
What's happening?
Oh my god.
Oh no.
Well, you're the one who finished it. You're the one who finished early. What else are we gonna do?
I'm actually stuck. I can't even move.
You can't move. Oh no.
No. Oh, here we go.
So I saw your email, Rohan. Yeah, that's.
Yeah.
Well. Did you notice that while preparing these talks, just while writing?